All right, welcome back for the lecture on matrix and vector calculus notation. Today we're going to do part one of the lecture. I'm Professor Wu, so let's get started. In the last class, we basically reviewed the basics of matrix and vector operations. All right, so I kind of briefly discussed why matrix and vector multiplications are important. Now we're going to look a little deeper of how we actually use them in machine learning. Well, in a big picture sense, vectors and matrix essentially enable us to compress very large equations. So, for example, let's look at a small equation to start off with. Let's say we have an equation that looks something like this. It's a pretty small equation with two input variables, x1 and x2, right? Given these two input variables, it has one single output. Well, it seems like we can convert this into a simpler vector format that looks like this, where A is a vector and X is a vector. How do we go about doing that? Well, think about it. If we let X1 and X2 be a single vector, and 2 and 3 be another vector, right? Then we can call the group of variables X, and we can call this A transpose. And therefore, what we have is A transpose X. Now, converting from here to this format is smaller, but you don't see that much of a saving, right? This is only particularly useful if we start working with very, very large equations. So, for example, in this case, we only have two variables. But what if we have a case where we have 1,000 variables? If we have 1,000 variables, well, without this notation, we would need to essentially write x1, x2, x3 all the way to x,000. But given this vector notation, we can represent all the numbers here as a single vector. And all the variables, we can group them into a single vector called x, A transpose. So notice that even though we have 1,000 variables, f of x can still be compactly written as ax, right? So you can compact two variables into the A transpose x, and you can compact 1,000 variables into A transpose x. So it doesn't matter. Now, it's our equation is agnostic to the size of the problem. It could be any size, and we can still compactly represent it this way, right? So, so here I said even 1,000 inputs, where we have a function that takes 1,000 inputs and spits out like a single output, can be simply written as this tiny little thing. Okay, so this is a really important tool and notation you need to realize, because these vector notations is what allows us to visualize and manipulate big data. Right? If you have a lot of data, you need a way to manipulate and visualize them. And right now, we're only dealing with a single output, where the function takes a thousand input and give single output. But the idea of compression of equation extends even if you have multiple output. So here you have a function of 1,000 input and 20 output. For example, like in those cases, the equation will be written something like this. So here's an example where we have equation with two input, right? You put x1, x2. However, it has three outputs, one, two, three. With this particular example, what we can do is notice that this can also be written as a vector, right? Once you have written this as vector, this is equal to 1x1 plus 2x2, right? That they're the same. And this is equal to 0x1 plus 1x2. And this one here is 3x1 plus x2. So we can write it in a vector format and can essentially maintain the same information. The reason why I make sure there's an x1 and x2 here is because this implies that we can pull them out. Notice how now we actually have a matrix where you have 1, 2, 0, 1, 3, 2, 1, 2, 0, 1, 3, 2, right? if we were, and then x1 and x2 are pulled out here. Once we have done this, notice how this is a matrix and this is a vector. It becomes a matrix vector multiplication because when we do matrix multiplication, this goes multiply. We basically have this and this, right? So once we do the multiplication and perform the dot product, is equivalent to this. We multiply and we add. That's where this addition comes in. Now, notice how this is a matrix. We can simply call this A, and we can simply call this X. And now we compress this pretty large, like multiple input, multiple output equation into something that looks just like this, right? This is a much more compressed. And like I said, this right here is only like 2 input, 3 output. You can imagine something with thousands of input, thousands of output. Regardless of the size, understanding this notation is what allows you to basically compress them, and then you can work on these like large matrices independent of their size. Okay. Another interesting thing is once you have it in this format, you can also plug any x in. So x, remember, has two variables, x1 and x2, right? x1, x2. So let's say we plug two variables in as the input. So this system, f of x, has two inputs, x1, x2, right? Now, and it has what? Three outputs, one, two, three. So if you plug x1 and x2, notice all you have to do is plug x1 and x2 here, and then, which is here, right? 1 and 1, 1, 1 and 0. And then all you have to do to get the result is perform a matrix operation. So what is interesting is we have a system of equations. Instead of solving the system equations, we can simply perform a matrix multiplication. A matrix multiplication gives us allows us to put some input and give us the output directly. And it's much easier to do a matrix multiplication than to deal with this. Okay. So the result of this, right, if you multiply this out, you should get 103. Okay. So the key takeaway here is that the matrix operation here, this multiplication of dot product, simulate the function. Right? It's basically acting as you putting some input and getting some output out. It's much easier way than solving it individually each equation. And the second takeaway is that matrix and vector operations enable us to represent big data. Right? No matter how big the data is, like we can have millions and millions of data, we can still represent the equation in this format, right? And allows us to essentially manipulate them compactly. So that's like in a nutshell, why matrix um, and vector multiplications are so integral for machine learning, because we have so much data and the only way you can manipulate them is through matrix operation. Okay, so your first exercise will be to practice doing this conversions. So why don't you practice converting these three equations, and then this over here allows you to convert back to these equations. So pause the video, and and we're going to continue. All right, I provide a solution here for you. Okay, so let's continue. Next, we want to find the derivatives with matrix and vector. So previously, we did the derivative with just a single variable x. X is assumed to be one dimension. But now we're going to assume that x is no longer one dimension. X is multiple dimensions, right? There are multiple variables within x. And we want to still take the derivative of with respect to x. And what does that mean? Well, okay. So before we jump into the meaning, we need to first realize there's two ways to symbolically represent functions of multiple inputs. Okay. So one way is method one. You can write f x1, x2, x3, right? And then basically you're looking at it saying this is a function of three inputs, and you can say x1, x2, x3 is within the function itself. Or another example, this function of two inputs, right? And this is great. You can put as many as you want. Once again, because we often deal with a lot of inputs, right? If you don't have a lot of inputs, writing it this way is great. But what if you have thousands and thousands of inputs? Then you will have to write something like this every single time, like 1 to 5,000. And that just gets annoying. So instead of writing this, it makes more sense for us to simply assume that x is just a vector and a vector of 5,000 variables, right? Notice the transpose. So this is a column vector. So x is a column vector of 5,000 variables. And then we just assume f of x can be one dimension or it can be multiple. Like that's to be defined, right? Of course, we'll write this will be like once you write this, then you will explicitly define how many inputs it take and what the output is. But in general, we don't have to assume x is just a single variable. In fact, from now on, we should start assuming that x is actually one or multiple variables. So we're just going to write, instead of 1 to 5,000, we simply write f of x. And f of x is just x1, x2, x3, right? There are three variables. And that is a much more shorter hand and more general representation of equations. Okay, so now we're ready to really start thinking about how to take derivatives in terms of multiple inputs. Okay, so we previously learned how to take derivative of this. This is just one variable. So x here is single variable, x, because there are no other x, right? Just x. So these are easy. We did this last class or previously. But what does it mean when x is no longer a single variable, but it's an entire vector of variables? Okay, so in this particular case, it's the same thing. Here's f of x, here is f of x, except x here is a single variable, whereas x here is a vector defined as such. So if you have a function of multivariable and you're taking a derivative, meaning that you're taking a derivative of this. Well, what's happening? Well, it's pretty simple. If you have three inputs, you simply need to take the derivative three times. Three times. Each time with respect to a variable. So the first one, you simply assume that x1 and only x1 is the variable, and everything else is a constant. Now remember what the constant rule is, right? Derivative of constant zero. So you can just only look at x1. And you repeat this process for x2 and x3. And then you will result in a vector of functions. So you will end up with like function 1. This function is with respect to x1, this function. So you have a vector of three functions if you had three input. Okay. So that's the key. Like you previously, if we have only one variable, it results in another function. But now, if you have multiple variables, it results in a vector of functions. Vector of functions. Okay. All right, so if we were to look at this previous example, we have three variables here, x1, x2, x3. So what is the derivative only with respect to x1? Well, there's no x1 here and there's no x1 here. So they are treated as a constant. The constant rule says that we can cancel them out, implying we only have to take derivative of this. So df dx1 is simply 2. Now, we continue the process with dfx2. Well, once again, x1 is a constant, x3 is a constant. So the derivative is simply minus x2, right? And once again, if we want to take derivative with respect to x3, they become 0. And now we take the derivative of this. So now, like I said previously, you end up with a vector of three functions. And then given these three functions, you can essentially at any given point of xyz, of x1, x2, x3, like you can pick any x1, x2, x3 and plug it into these functions. If you plug this into this vector, then you're going to get like three numbers. So for example here, let's say we want to know the derivative specifically at this point, 1, 0, and 1, okay? And now we plug x hat into each function. So if we plug x hat into the first function, well, it doesn't matter, it would just be 2. If we plug x hat into this, there's only x2 in there. So what was x2? 0. So that will give us minus e to the 0. Again, if we plug x hat into the third one, well, if we plug x hat, they need x3. x3 is 1. So we plug 1 here, essentially giving us this. So now we know the derivative is 2, -1, and -1, implying that at this point, at this exact point, if you were to increase x, then you're going to increase the function. If you were to increase a little bit of x2, you're going to decrease. You're going to decrease because it's minus the function. And at point 3, at this exact point, if you were to increase x3, you're going to decrease the function. So it's telling you exactly how you tweak each function, it would manipulate the outcome of the function. Okay? Okay. So as a general rule, is that the output of the derivative function is always the size of the input. And that makes sense, because if you have multiple inputs, you need to know how how when you tweak each input, how it's going to impact like the output, right? So the function itself is defined as a function that takes d dimension and outputs 1 dimension. However, after you take the derivative function still takes d dimension in, but it outputs d dimension out. Okay, d-dimensional as a vector. And this can also be visualized this way. So remember, in one dimension, you only look at x. As x increases, how does it impact y? Is it going up? Is it going down? But when you have multiple directions, so like this particular example here, right? So you one direction, you need to know, as x increase, how does it impact the function? As y increases, how does it impact the function? So you can kind of keep this mental image in mind. That it's like, and then you goes higher and higher dimension. So okay, so now let me do a quick aside before we move on, that some of you may have like a little confusion with this. So sometimes we need to take the derivative with respect to summation. Okay, so a quick review: a summation here from 1 to 3. What that's saying is, you have, notice the I here. That means is summing alpha 1, alpha 2, alpha 3, because it's going from 1 to 3. So it's like a loop. It's iteratively looping, and then each one of them is multiplied by x. So what this is saying is, you're taking the derivative of this, taking the derivative of this. That's what that's saying. And when you take the derivative of a summation, like, obviously you can either just write it out. So the first method, you can just write it out. So write out the whole sum. After you write the whole sum, you take the derivative. So we can use the sum rule. So derivative here is alpha 1, right? Alpha 2, alpha 3. So, and then you notice how this is equivalent to the summation of alpha I. So alpha I from 1 to 3. So that's you can do that, but that's a bit slow. The ideal way is for you to realize that when you're taking the derivative, you can actually move it inside, and just kind of deal with that later. So you're really taking the derivative with respect to x and alpha, and then alpha I is a constant. So when you do this, x cancels out, right? So resulting, the summation is still there, resulting alpha I. So that's how they are the same solution. Okay, so that's a quick aside, just so you realize the derivative can just move inside the summation. All right, now I think, I think this is the final practice for the day. So we want to quickly consolidate what we just learned. Oh, interesting. Yeah. So basically I want you to go over this and pause the video. And I think that's it for today. Yeah, these are the solutions for this. So I want you to go over this really quickly and basically like make sure you can do this. Okay. I think in the next lecture we'll move on to part 2.